Hello everybody, so today I'm just going to talk you through some of the AC current questions from the Physics Plus textbook, including some questions on transformers, mutual induction and self-induction. So we'll start off with question 1. For question 1, it's giving you a peak voltage value for an AC power supply, and they're telling you the peak value is 330 volts, and they want you to find the root mean square value. To solve this, we're just going to use the formula that the root mean squared voltage is equal to the max voltage, which I've already put down here as V0, but you can use either. The max voltage divided by the square root of 2. Now we can fill in the max voltage there is 330, divides by the square root of 2, and that will give you out your answer. For question 2, it's a similar question, but we are given the root mean squared current. And they want us to find the peak current or the maximum current. So again, we're going to use a similar formula. The root mean square is equal to the max divided by the square root of 2. And we're going to fill in 7.1 here. That's going to equal to the max current divided by the square root of 2. And then you solve that to find your max current. For question 3, they want to know one reason why the main supply is alternating voltage. Well, it has to be, first of all, because the generator in the power plant is going to create a alternating current just because they're spinning a copper coil inside the magnet. So as the copper coil is moving one way, it's going to create a current in that direction. Here's our copper coil, and then when it starts flipping the other way, it's going to create a current going in the opposite direction. So because it's constantly rotating, it's going to send the current back and forth. A second reason that we know it's going to be an AC current is because in the national grid, they're relying on transformers to bring current from the power station to our homes. So the power station, I think, creates power at about 500 volts. And it reaches our home at 230 volts after being transferred at about 40,000 volts. So in order to get it from 50 or 500 volts up to 40,000 volts, we need to use a step-up transformer, which increases the voltage, and then to go from 40,000 volts down to 230 volts, we again need to use a transformer, this time a step-down transformer. Step-down transformer just takes a voltage and makes it lower. Transformers will only work with AC current, so the power supply to our home has to be AC current. For question 4, we are given the number of primary and secondary turns in a coil. We're given the input voltage, so the voltage in the first coil, and we're asked to find the output voltage of a transformer. So we're going to use this formula here. All this formula says is that the ratio between the number of turns in the primary and secondary coil is the same as the ratio of the voltages in the primary and secondary coil. So if you go from less turns to more turns, you're going to go from less voltage to more voltage, or vice versa. So when you fill your values into the formula, you get this. And you should be able to solve that out to get the output voltage. A handy way of doing that mathematically is just to cross multiply. So you'll get 200 times the second voltage equal to 12 times 50, and you can solve from there. So for question 5, we're just told that an American device will use 110 volts as its input voltage, and an Irish plug socket produces 230 volts. So a transformer or an adapter to go from Irish mains to an American device will be taking 230 volts of power supply and changing it to 110 volts. So we're asked if this is a step up or a step down transformer. It's a step down transformer because it takes a higher voltage and makes it lower. For question 6, we're going to be using this formula here again. The ratio of the turns in the secondary to primary coil is the same as the ratio of the voltages across the secondary and primary coil. So when you fill it into the formula, it will look like this. And again, you just want to solve for your unknown variable there, then the number of turns of the primary coil. Now in this one they ask you, where might such a transformer be used for part B? I think that a good answer to that question would be that it would be used in the national grid as a step down transformer to take energy from the power cables, which is at a higher voltage, 44,000, to a lower voltage like 230 volts, which is actually the voltage that goes into our homes. So I think that's the answer they're looking for here. So question 7 talks about a transformer which is going to turn 20,000 volts to 40,000 volts, so it can be transferred to a distant city. First of all, they ask you, is this a step up or a step down? It's going to be a step up transformer because it increases the voltage. For question 7 part B, we're asked if there was 10,000 turns in the primary coil, how many turns do you need to have in the secondary coil? So you can fill in the information again into this formula. The ratio of the voltages is the same as the ratio of the turns. Again, cross multiplying might be a nice option here. A handy shortcut you can use is just realizing that 40,000 divided by 20,000 actually simplifies to 2 over 1. And this might make your calculations a little bit easier. So for question 8, you're going to use a very similar method. I think at this point I don't need to talk you through how to select the secondary and primary voltage and secondary and primary number of turns. You can probably have a go at that yourself. Question 9 starts off pretty similar, asking you to find the output voltage in a transformer. So again, you just fill in the terms you're given and try and find then your unknown value, which will be the voltage of the second coil. Question 9 part B really stretches your understanding of transformers. What it does is it gives you a current in the primary coil and it asks you to find the output current or the current in the secondary coil. So using our understanding of transformers, we can actually change the formula a little bit. So we're going to keep something that looks very similar. So if you look closely here, you'll notice a couple of differences. One of them is that I've switched the voltage in the primary and secondary to being the current. But the second thing you might notice is that the primary and secondary are switched. So what this means is that if the number of coils is increasing, like in a step up transformer where the voltage would increase, then it's going to have the opposite effect on the current. This ties back to Joule's law that the total electrical power is equal to the voltage times the current. So if one of these goes up, then the other one goes down. Basically, that voltage and current will have an inverse relationship when the power is kept constant. So it is again very similar to the formula for the voltage across the transformer, but it's got the inverse relationship. The primary and secondary current are switched with the primary and second voltage. So filling this in now, we know the current in the primary coil is 0.4 amps. asked for the output current or the secondary current. We know the number of turns in the second coil is 200 and the number of turns on the primary coil is 2000. So again, at this point we can use our algebra skills to solve for the output current. Again, cross multiplication can be a really handy way of doing this, and you might notice that's a pretty easy fraction to simplify first over here on the right hand side. So in question 10 we're given a circuit that has a transformer in it, and we're asked to find the primary current and the secondary current. Now, and if we look at the primary part of the circuit, we know the voltage, which is 230 volts AC, but we do not know the resistance, so we can't figure out the current. If we look at the secondary part of the circuit, we know the resistance, but we do not know the voltage, so we also can't figure out the current there. So a good place to start is try and see what we can figure out, and that would probably be the voltage across the secondary coil. So again, we can use this formula here. The ratio between the voltages will be the same as the ratio of the number of coils. This will give us the following answer. So we fill it in, we get this. 20,000 divided by 2,000 actually simplifies to 10 over 1. So again, we can cross multiply. Secondary voltage times 1 is just the secondary voltage. 230 times 10 is 2300 or 2300 volts. At this point now, we know the secondary voltage and we know the resistance, so we can use Ohm's law to figure out the current in the secondary coil. So this will give us an answer of 5.75 by 10 to the minus 3 amps. Now, in order to get the current in the primary coil, at this point, all we have to do is remember our slightly amended formula for the current in a transformer. So it's just like the voltage formula, but we just inverted for current, because if the voltage is going up, the current is going down. So the primary current divided by the secondary current equals the number of turns in the secondary coil divided by the number of turns in the primary coil. So when we fill that in, it'll look something like this, and then we just solve it for unknown value, which is the current in the primary part of that circuit. Question 11a is quite similar to a few of the ones we've already seen. It's just asking about the number of turns on a secondary coil, so I won't go through that again. What I do want to talk about question 11b, because it does a little bit of revision towards our power formula, which says power is the product of voltage and current. And that's not how we define power, but it is a useful formula for electrical appliances. So they talk about a charger being left plugged in, and they want to know how much electrical energy is used over a 24-hour period. Now, if we just look at the primary coil, or the primary circuit on a transformer, it tells us that it's got a 230 volt supply that it's connected to, and that the current in the primary coil is 0.2 A. So that tells us that our total power is going to be equal to 46 watts, or 46 joules per second. Now, if we want to mathematically represent the relationship between energy and power, we would do it using the following formula, that power is the rate at which work is done, or the rate at which energy is converted from one form to another. Rearrange this formula and we get energy is equal to power multiplied by time. So we've got the power here in watts, and we want to convert that to energy. So we're going to fill in 46 watts, and we just need to figure out what our time is in seconds first. We're asked about 24 hours. So 24 hours, we're going to change that first of all to minutes and then to seconds. So to change it to minutes, I'm going to multiply it by 60 because there's 60 minutes in an hour. So that will give us 1,440 minutes. Now we're going to multiply 1,440 minutes by 60 again to get the number of seconds in 24 hours. So that gives us 86400. So if we go back to our energy formula there, we're going to fill in the power as 46, and we're going to fill in the time as 86400. Again, what we did there was make sure to just convert 24 hours into seconds because that's the standard unit for time. So if we multiply that out, we get 3,974,400 joules of energy. So in question 13, we're presented with a light bulb with a coil parallel to it and a switch in the circuit. We're told that it's a DC circuit with a EMF of 12 volts. Now the light bulb needs 60 volts to light. So obviously when this is closed, the light bulb is not going to light up because there'll only be a potential difference of 12 volts across the light bulb. But they mentioned that when the switch is open that the bulb briefly lights. So what happens is when the switch is closed, current will flow through this coil. When the switch is open, then current will stop flowing obviously around the larger circuit, but what will happen is a smaller circuit is created here. Now because current goes from flowing to not flowing, there's a change in current here, which will in turn change the magnetic field around this coil. That changing magnetic field will then induce another current or another EMF, which will cause a current. But now it's part of a smaller circuit that just extends around here. Again, this process is called self-induction. But the EMF that's induced now at this point must be big enough to overcome that 60 volt potential difference required here. Otherwise that bulb would not light. So that'll happen momentarily because of the changing current causes a changing EMF or changing magnetic field, which then induces an EMF. But then once that circuit has been opened and remains open, there's no longer going to be any reason for this current here to change, so we won't get a continued EMF to keep this bulb lighting up. So now we're going to quickly look at question 14. Question 14 describes an AC circuit that has a coil and it has a bulb in it. The bulb lights up, but they say that when a metal bar is inserted into the coil, the bulb becomes less bright, and they want to know why that is. Well, the key to understanding that is understanding the idea of self-induction. So what happens here is the alternating current is going to create a constantly changing magnetic field. The constantly changing magnetic field will induce an EMF across this coil here, which will actually act because of Lenz's law to resist the magnetic field that's causing it. So what we'll see is if this was, say for example, a potential difference of 5 volts, we might actually get a backwards potential difference of 2 volts here, giving an overall potential difference of 3 volts. So this acts in many ways like a resistor because of self-induction. When a iron bar is inserted into the coil, it actually increases the effectiveness of self-induction. So if this is acting like a resistor, by putting a iron core into the coil, you increase the resistance by increasing the self-induction. And with a increased resistance, obviously the bulb at that point then is going to become dimmer. So that's really the explanation there for question 14. Interestingly, this is actually how a dimmer switch works on a light switch. So as you rotate the dimmer switch, a iron core is moved in and out of a coil, which then changes the resistance and changes how bright the bulb is actually going to be. So for question 15, we see a very similar circuit. We have an alternating current with the 5 volt voltage. We are told that there is a current flowing in the circuit of 0.2 amps. And we're told the resistance of the bulb is 15 ohms. And we're asked to find out what the induced EMF in this coil is. Now, the way that I think we could go about that is by trying to figure out what the effective voltage is in this circuit. So we know that there's a voltage of 5 amps applied at the mains or at the cell where it's hooked up to the mains. So now all that we're going to try and do is figure out, well, what's the effective voltage? So if we use Ohm's law, say for example for this bulb, V equals IR, and we're going to multiply the current 0.2 times the resistance, which is 15. So that gives us an effective voltage of 3. So what this means for us then is there is a potential difference of 3 volts across the circuit, even though there's been 5 volts applied. So the reason for that difference then is that there must be a backwards EMF of 2 volts working in the opposite direction to the 5 volts that's being applied there where it's connected to the mains. So again, 5 volts is the actual potential difference applied to the circuit. A backwards EMF there of 2 volts will leave you with an overall potential difference of 3 volts in the circuit. So your answer is just 2 volts is the backward EMF.